Hello students, this lecture is lecture 21. We will be covering an abridged version of chapter 5. We will talk about natural radioactivity, the radiation measurements. We will talk about half-life calculations, and lastly we will end with health-related applications for radioactive materials. So let's start this chapter with reviewing a little bit about what are isotopes. Remember way back when we learned about isotopes. Isotopes were basically atoms of a certain element that differ in the amount of, not protons they have, but differ in the amount of neutrons they have. Right? So for example, I have here iodine. Iodine has atomic number 53. Remember that means then that iodine has 53 protons. Iodine, for the most case, has a mass number of 127. That's the majority of them, has a mass number of 127. It turns out there are other isotopes of iodine. For example, iodine 125 has a mass number of 125, and iodine 131 has a mass number of 131. Remember that the mass number is basically the number of protons and neutrons plus together. So iodine 125 would be an iodine atom that has 53 protons, but how many neutrons? Let's do our calculator. 125 minus 53, that would be 72 neutrons, right? So again, that was just a little bit of review of isotopes. Now, why did I highlight all of these isotopes in different colors? Well, it turns out the ones I've highlighted are what is known as radioisotopes. That means these are isotopes that are radioactive, okay? Or the definition of a radioisotope is that it is an isotope that is an unstable nucleus. What does unstable nucleus means? That means it will just randomly break apart, and when it breaks apart, it will emit out these small particles. Remember what's in an atom, right? You have your protons, your neutrons, and your electrons. You have positive and negative charges, and you also have masses. So when it breaks apart, it will release these particular parts. Now, the type of parts that it releases will define the type of radioactivity. Okay, so it will emit this energy we call radiation. And so, what are the types of radiation that we will learn in this class? We will learn about alpha particles, we will learn about beta particles, positrons, and gamma rays. So alpha particles, let's see. What is an alpha particle? An alpha particle basically means that it's a particle that has 2 protons and 2 neutrons. Now think about that. What is 2 protons and 2 neutrons? That's basically identical to a helium nucleus. Now why did I say nucleus? Remember that a helium atom will have 2 protons, 2 neutrons, and 2 electrons, right? So that would make an atom. In this case, it's not a helium atom. It is similar to a helium atom because it releases 2 protons and 2 neutrons without the electrons. So because it's a little bit different, we call it an alpha particle. So in essence, when that isotope breaks down, it will release a helium atom without the electrons. Okay? So the alpha particle are very high in energy because why? They are very large compared to the other radio particles that we will be discussing. Because they are so large, they won't travel very far. Why is that? So imagine in the atmosphere there are lots and lots of molecules, gas molecules, right? So if something that's very big, it won't travel very far until it hits a gas particle. And once it hits a gas particle, it's going to transmit its energy into that gas particle and maybe take some electrons from that gas particle. Once it takes the electrons from that gas particle, for example, then it will no longer be an alpha particle. It will just be a helium gas, right? The helium atom floating around. So that's why it doesn't travel very far. Just imagine if you were in a field, right? If you were running down that field empty of people versus you were running down that field with tons of people, which one would you travel farther in? Tons of people or no people, right? You will travel farther if there's no one to kind of block you. Same thing with this alpha particle. Because it's so big, it will bump into another atom very easily. What is its biological damage then? Well, because it is so big and so high in energy, it is very damaging if it is in your body. If it is outside your body, if that source is outside your body, it turns out it's not going to be that damaging because, again, it doesn't travel very far before it hits a gas molecule. Therefore, it's not going to hit you. Okay, so that's why it's not going to be super dangerous unless you have it in your body. The next particle we're going to talk about is called the beta particles. And I'm going to group this together with the positrons because they're basically opposite of one another. Okay, so what happens when you release a beta particle is if you have a neutron in your nucleus and all of a sudden it turns into a proton. And once it turns into a proton, it has to release this particle called the beta particle. Now let's think about why that is. So remember what a neutron is. Remember that the number in the bottom represents the number of protons, whereas the number on the top represents the mass number, the number of protons and neutrons together. So if you're just a neutron, your number on the bottom is going to be 0 because you don't have proton, whereas your number on top will be 1 because you have 1 neutron. 1 plus 0 is 1. Now, again, in this case, your neutron will turn into a proton. Remember that a neutron is neutral, right? So how would it turn into a proton? If a neutron releases a negative part of itself, releases -1 charge, it will become a +1, right? Remember that a neutron has the same mass as a proton. So if it's the same mass as a proton, but now it is +1, it is basically a proton. Okay? So again, when a neutron turns into a proton, it releases a beta particle. So what is a beta particle? You can think about a beta particle is just like an electron, right? It has very small mass, but yet it has a charge of -1. What does that sound like to you? An electron, right? But why don't we call it an electron? Well, because where do electrons live? Electrons live outside the nucleus. Where is this beta particle coming from? It is coming from inside the nucleus. Because it's coming from inside the nucleus, we give it a new name called a beta particle. All right, so that's all the notes I had. So electrons from the nucleus has a -1 charge. It happens when a neutron transformed to a proton. As a result, it releases this particle that is like an electron from a nucleus, so we call it a beta particle. A beta particle is very small, so it can travel very far in the atmosphere. It can travel 1 meter in the air before it hits something. So in terms of being safety-wise, you want to be not too close to the source of a beta emitter. Because it's very small, it can pass through your clothing, so your clothing won't protect you. But however, it's big enough that it will not pass through metal. So if you're wearing metal, the beta particles cannot go through that sheet of metal. Okay, now let's turn our attention to positrons. So positrons are the opposite of beta particles. So remember that a beta particle is when a neutron becomes a proton. Well, a positron is when a proton spontaneously become a neutron. So let's think about that again. A proton is a positively charged species with 1 AMU. Now, so how do I make it to become a neutron, which is a neutral species with 1 AMU? So the mass hasn't changed, but the charge did, right? So you are +1. How do you become neutral? You would have to release your positive charge, right? So yes, so once it releases this positive charge, remember, if you're releasing just a positive charge, you are not a mass. What does not have mass? An electron doesn't have mass, not a lot, right? So you're releasing something that is like an electron, but with a positive charge. So it's basically a positive electron. Because of that, we give it a very original name, positrons. Okay, so again, simply, it is a positive electron emitted from the nucleus when a proton is transformed to become a neutron. Okay, and our last radiation particle is called the gamma rays. Gamma rays are very different from the other three because they do not have mass. They are very high in energy, and they are chargeless also. Because they don't have mass, they're just waves, right? So they travel very far and penetrate very deep. They can go through metals unless that metal is very thick. Gamma rays can come from the cosmic rays. So right now we're experiencing a lot of gamma rays. And as we go farther into space, we will experience it more. Luckily, we're down here, so we have layers of clouds and layers of atmospheres to protect us a little bit from the gamma rays. Now, let's talk about the biological effects of radiation. So what happens is when radiation strikes a molecule, it will knock away an electron. When it knocks away an electron, this is why it is dangerous, because it is forming an unstable ion. Remember, a neutral molecule is neutral, but if it's losing an electron, it is no longer a molecule. It becomes an ion, right? So these ions actually will interact with the water molecules in your cells, in your body, and it will form a very reactive molecule or ion called H2O plus, something that we haven't seen. We only seen H2O. It's neutral, but this one electron is popped out, so it's H2O positive charge. Now this guy can form things like toxic peroxide, or even it can interact with your DNA and break the bonds in your DNA. So why is DNA damage a bad thing? Well, remember that DNA is what is needed when your cells replicate, right? That's the blueprint to tell your cells how to replicate itself. Now, so if your DNA is damaged, then your cells have mechanisms to repair that. So either they can repair the DNA damage and you go on reproducing or replicating your cells regularly, or when your DNA cannot be repaired, there are other mechanisms in your cells that come and kind of recycle or kill your damaged cell. So those two things are actually good for you. However, sometimes neither of these things happen, and therefore you will have a mutation in your cells. And the mutations are bad because then they can't be regulated. For example, they might not regulate the growth of your cells, so you keep on growing, and that's how tumors are, unregulated cell growth, right? And that's all because stemming from DNA damage caused by, one example is from radiation. So the cells that are most sensitive to radiation then are cells that are always undergoing cell division, because if you are always undergoing cell division, you really need good DNA, the intact DNA, right? So that's why parts of your bodies that are very susceptible to cancer is related to your blood, gastrointestinal, and your reproductive organs. Okay, less sensitive, so you see less problems with these from radiation is like skin or muscle. And actually, cancer cells themselves are very susceptible to radiation damage, which is kind of, right? That's why you undergo radiation therapy to kill, sometimes to treat cancer, to treat the tumor, because it does kill tumor cells. It does kill cancer cells too. But it's a kind of funny cycle because it can cause cancer, but it also is used as a treatment. So it all depends on the tool that you use, or how you use that tool, in this case, the radiation. And again, we mentioned that radiation can cause cancer, and that's why we need to protect ourselves. I try to show that with having this shield in front of Homer that represents a typical, that represents a typical person, right? So let's see how we can protect ourselves. Because remember, Homer works at a nuclear power, which is basically a plant that produces energy from radiation, nuclear chemistry. Okay, so how do we protect ourselves? Remember that to protect ourselves, we don't want the radiation to penetrate into our body and to get into our cells and DNAs, right? So depending on the radiation particle that you're dealing with, you would have different measures of protection. For example, if it is an alpha particle you're dealing with, then simply things that are thin as paper or clothing is good enough to protect you. Whereas if you're dealing with a beta particle, a little bit smaller now, you would need to wear lab coats and gloves in order to protect your body. Going beyond that, going to gamma rays, remember those things do not have mass. They are basically energy, so they go through a lot of things. You would need to protect yourself with a thick shield, usually a lead shield or even concrete. So this is similar to, as you can see in your everyday life when you go to a dentist, when they take an x-ray of you, what do? They go and go away from the source, right? They go into the other room and where they press that button, so they'll get exposed all the time because they're doing that every day, every minute of the day. Well, not every minute, but a lot of the minutes of the day. But what do they put on you also? A very thick and heavy vest, right? That's to protect your organs when you are being taken the picture. You'll be exposed, but they want to protect your organs. Okay. Now that sounds a little dangerous, but again, the poison is in the dosage. A little bit radiation will not harm you, but radiation over time constantly will cause the damage, right? Because a little damage the body can repair, but a lot of damage the cells cannot repair that, and then leads to problems that we just talked about.